This is a solution to one of the homework problems in section 6.2 where we need to make the slices horizontally. We can tell that that's really what we should be doing for a couple of reasons. First of all, the curve that's given in this problem is a parabola that's given in terms of x. So it says x equals a function in terms of y, which means it's going to be a parabola that opens left and right instead of a parabola that opens up or down. So that's one clue. The other is in the picture, we can see that if I were to draw a horizontal slice, then regardless of where I draw that slice in the gray region, the right-hand side of that slice is on the line and the left-hand slice is on the curve. And so that means that it's going to be easy to describe an area approximation for one slice by using the same coordinates on the same formula for the the same formula on the right side as on the left side. The alternative would have been to slice it vertically, but you can see that if I do a vertical slice, it'll work okay, but even just these two slices are composed slightly differently. The left slice has both of its endpoints, top and bottom, on the parabola. The other slice that I drew has its top on the line, bottom on the parabola. So if I use the slice on the left, if I use vertical slices, then I have two issues. One is that the coordinates of the top and bottom of the slice use different formulas depending on where the slice is. And the other one is that the equation of the parabola is not written the correct way around for me to do that easily. So I'd have some more algebra to do. So the problem as it's given is easiest to do with horizontal slices. So when I make a horizontal slice, the location of that slice is going to be given by a y-coordinate. And so that means everything about this problem is going to have to be done in terms of y. So if I label the coordinates of the left and right hand side of this slice, what I know for sure is that the y-coordinate at both ends of this slice are the same. And so that's what I'm going to use my variable y. Which means I need to figure out what the x-coordinate is in terms of y. The equation of the parabola is actually given that way. This tells me the x-coordinate is always the y-coordinate minus 3 squared over 5. So this tells me how to get the x-coordinate from the y-coordinate. And so that's exactly what I would need to have here. So the formula for the x-coordinate is given in that problem, in the problem. This is not given that way. This does not give us x-coordinate equals something with y's, but it's very easy algebra. If I add x to both sides and then subtract y from both sides, then that's an equivalent equation, and now that does give me the x-coordinate in terms of the y-coordinate. So that's what we'll go here. So notice that it's a complete coincidence. The symmetry of this is a complete coincidence. I have to solve this for x, and it just so happens that in this particular line, solving it for x really is, it feels like you're just switching the x and the y in the original equation. That's not really what's happening. You're really algebraically solving for x, whatever it is. And so now I know the x-coordinates of the two ends of this little slice. So the area of a single rectangle that approximates that slice is going to be the length of the rectangle, which is the difference in the difference in the x-coordinates. This is a horizontal rectangle, so the length of it will be the difference in the x-coordinates. And the thickness will be just delta y. As usual with our theory, the sum of the rectangles is our approximation, and then in the limit, the sigma becomes the integration. This formula for height or length of the rectangle is exactly as written, and the dx becomes dy. So the only issue remaining is what are the limits of integration on this? And notice this graph is not labeled, so they're not giving me that in a problem, so they're making that part of the problem, which is not hard. It's just not really calculus. It's algebra. To figure out the points of intersection, I just need to have these two things equal to each other. Remember, the logic is, the thought process is, because both of these equations say x equals something, then a point of intersection is going to be a point where the x that it refers to, the x coordinate refers to, is the same on both curves. When you have your x and y coordinate the same on both curves, that's what an intersection point is. So if the x coordinates are the same, that means that the x in this equation is the same as the x in this equation. And so we can actually set these two expressions equal to each other. So the thing that the x is equal to in the first equation has to be the same as the thing the x is equal to in the second equation. And I just need to solve that. It'll be, you've got to multiply both sides by 5. You're going to have to do some FOIL here to multiply that out. It'll end up being a quadratic equation, but it does end up having nice answers. For this particular one, if you want to try it and see, I got y equals -7, y equals 8. You don't need to watch me do it, but that's what I got when I did it on paper. So those are the limits of integration. If I could ever, I guess I can't erase anything. All right, well, fine. So -7 to 8 are the limits of integration. So that's my integral that will work for this problem. It is possible to have set this up in terms of x, but like I said, you'd have to break it into two problems and you'd have even more algebra to do. So setting it up as horizontal slices is definitely the easiest thing to do. And so now we have, it's a 5. So that's the integral we have. If you wanted to, the next part of the problem is going to be to actually evaluate that integral. Obviously, the thing squared and the fraction is really the main issue here. So I would just say, first of all, I would just resolve all of that. So I'll go ahead and do that algebra for you real quick, and then you'll see that it's sort of normal stuff. If I got a common denominator of 5, then that means this first part is going to be 65 minus 5y over 5, and then that's going to be equal to this other part over 5. And the other part, if I do FOIL, sorry, I got the wrong pen today. If I do multiply out that thing that's squared, then that's what I'll have. So I'm sort of blowing the whole thing up. And the reason I'm doing that is because I really don't want to have to do substitution or anything sophisticated when I can see this is just going to be a polynomial. Polynomials are always the easiest things to do, even if you have to expend a little energy on the algebra beforehand. So I would this denominator 5, I would just pull out front as a 1/5, so I don't have to think about it. And then everything else inside, I have to just resolve the this subtraction, right? Don't forget the parentheses going on here. So so 65 minus 9 is, why do I think I can do that? 56. Minus 5y minus 6y is plus y. And I have a minus y squared. So if I spend a little bit of energy on the integrand with algebra, then I end up with an integral that's actually pretty easy to do. And that's much easier than trying to do some kind of fancy substitution throughout this guy. If you want to do this one to the end, for this particular one, I got 225 halves. If you want to check it, see if you got the integral right.